So first of all, I'd like to apologize because I did have some videos for you guys yesterday and I totally forgot to post them because I'm not in the habit of doing that. So today I'll talk about what was in those videos, and you can watch them today to get more understanding of the topics. First, some bookkeeping stuff though. So talking to the PM was about who has gotten how far in the first couple days. Uh, it seems like a lot of people got hung up on quicksort. And I didn't realize this at the time, but other cohorts before you had already had quicksort as a code challenge, which is part of the reason it was in here. Just go get your old JavaScript quicksort and port it. But apparently you guys did peer reviews on that code challenge today instead. So that made quicksort much harder. So apologies for that. So I'm going to write this up and I'll put it in the channel for the record. But here's what I'm thinking for the next couple days. So we kind of did intro to C stuff the first couple days. Now we're going to do a little bit of applied C in an operating system context. We'll do that for a couple more days. And we have 6 exercises in this repo that are similar to the exercises in the previous repo, except I think a lot less brain bending. There are some new topics in there, but the topics aren't that hard. So what I'd like to do is pause what you're doing on the previous repo if you haven't finished it yet. And then we'll start on this repo today. And if you have time at the end of this repo, when you finish this part, jump back to the first one. If that sounds good, I don't know, does that sound reasonable to people? Give me a thumbs up or thumbs down in the channel. And then I have one more piece of information on that. I would like to move quicksort to the end of that first repo. So if you're stuck on it, skip it, because I'd rather have you look at malloc and struct, which are two relatively simple concepts. Malloc is all about memory allocation. You haven't done that before because JavaScript always takes care of allocating memory for you, but in C you have to be more explicit about it. And also structs are very similar to what you're used to as objects in JavaScript. They're kind of analogous to that. A little less flexible, but similar. So that would be good exposure to have. Plus, we use some structs in the work we do today, or today and tomorrow, I think. So again, I'll write all that up and put it in the channel, but I just want to throw it out there. If anybody has any misgivings about that approach, go ahead and DM me or just yell at me in the channel. That's fine too. All right, so this next part of the week is all about operating systems. And this is my chance to kind of talk about this. And this is my chance to talk about this. That's kind of a nondescript thing to say. Like every lecture I've ever had. Let's see here. What I meant by that was we do a whole sprint on computer architecture. So we talk about the super low level stuff in that sprint. And this whole time you've been working at Lambda School, you've been kind of up at this higher level working on JavaScript stuff. And so between you at JavaScript level and the machine that's doing the work, there are a whole pile of layers in there. And it's kind of opaque. If you're working at the JavaScript level and you're getting your stuff done and you're sending things out with Express and so on, like you've learned these patterns for programming that get the job done. But what actually happens deep down inside the computer when you set up an endpoint with Express, that's pretty opaque. Like you don't actually know what's happening way down there. And that's kind of by design. When you're programming something like a web server, you don't want to have to think about all that super low level stuff, because it's painful. And so programmers that have come before you have built these layers in place to separate you from the nitty-gritty details of the machine and to make your lives easier, to make it so you can be more productive at doing software development and you can actually get projects out the door in a reasonable time frame. It used to be, in the good old days, if you wanted to write a web server, that was a major undertaking. For a while, when it first started, there was only one program in the world that was a web server. It was like the first one that came out. They're like, oh, here's a web server. We wrote it very painfully and painstakingly. Now, if you guys want to write a web server, you write like a few lines of Express and you say go, and you have a web server running just like that. So all of that pain has been isolated and hidden away from us underneath all these layers that make the nice, soft, cushy bed that is modern programming. And of course, this last week, these last couple of days, we've been kind of looking down there a little bit and seeing what it's like deeper down underneath all these layers of abstraction. And you're probably thinking, man, there's some crazy stuff here. I got to worry about pointers. I got to allocate my own memory. Like, why do I have to do all this stuff? And people have had exactly that question. Why do I have to allocate my own memory? Why do I have to do this stuff? And in order to solve that problem, things like Node were invented, right? Languages with garbage collection were invented. People are like, we're tired of managing our own memory, dealing with that headache and all the bugs that come along with it. So let's invent a new language that makes it so we don't have to do that anymore. And every time we do that, it gets easier and easier to build something bigger and bigger. So I'm eventually thinking that sometime we'll be in the Star Trek universe where you just talk to your computer and you ask it to write a program for you, and then it does. Maybe someday. But until then, we all have jobs, so that's good. Anyhow, I apologize for going on for so long. This is just the lead up. I'm like the, what do you call the guy that comes out before the main show? I guess he's the MC, right? The warm-up comedian. I'm my own hype guy. So in terms of talking about these layers of complexity, one of the things that's intertwined with this idea are the layers of software that exist on your computer. And deep down, we haven't talked about this yet, but deep down we use machine code and assembly language. Like really deep down, we're just talking about voltages on wires that are making this machine work incredibly. Both voltages on hard wires or on wires are hard for humans to read. So we've abstracted that into assembly language, which is just like one tiny little step above it, but slightly human readable. But that's a pain. So somebody wrote C so that we wouldn't have to write assembly. But that's a pain. So somebody wrote other languages on top of C so that we wouldn't have to write stuff in C anymore, and so on. But between us and that hardware is something called the operating system. And that's what we're going to talk about these next 2 days. And we're going to discuss how the operating system fits into our entire stack of computing that we're using. And we're also going to ask the operating system to do stuff for us. We're going to write some C programs that talk directly to the operating system and say, hey, get this done. First, an easy question. What's everyone's favorite operating system? Maybe you've only used one, and that makes it your favorite. iOS, Linux, Mac OS. I asked for favorite. I didn't ask for best. That would have been different. I didn't want it to turn. We joke in the motorcycle world that if you ask people what motor oil they should use, it's just like you get every single possible answer, and everybody thinks everybody else is wrong. Elementary OS. All these OS, nobody mentioned Windows. Nobody's gonna go there. Android. All the OSs mentioned so far have something in common. So iOS, Linux, Elementary, Android, Mac OS, they all have a common, I shouldn't say a common ancestor, but they're all what we call Unix-like operating systems. So there was an operating system back in the day called Unix. Still exists, I think. Unix is a trademark owned by AT&T of all people. So you can't just make an operating system and call it Unix, even if it looks just like Unix. You have to call it something else. So we call it Mac OS, or we call it Linux. There's another one called BSD, Berkeley Software Development. I can't remember what BSD stands for. These are all Unix-likes, we call them. Windows is not a Unix-like operating system. It's its own thing, which kind of burns me because Microsoft actually owned the rights to a Unix-like operating system called Xenix back in the 90s. And they gave that up. The idea was that they were going to take Xenix and turn it into a more capable multi-user operating system to take the place of MS-DOS and simple Windows 3.1. But instead of running with Xenix, they decided to roll their own. They made something called Windows NT. And Windows NT is okay, but as anyone who's done any of this software development stuff on Windows can attest, there's some weird stuff that happens. And Microsoft, in their defense, is trying to fix things up with like WSL, so make it easier for developers to work on Unix-likes by embedding their own little Unix-like inside it. But it's been a long haul. Palm OS. Oh, Palm OS. I know what Palm OS is, but not Palmo. 1.0. I wrote software for Palm OS. Not a Unix-like. Anyway, let's talk a little bit about what OSs do. Why they exist. Does anybody actually know off the top of their head? It's kind of an open-ended question. I have a good one-sentence definition of what operating systems are that I like. Got a nice user interface. Schedule system processes. Yeah, these are both things that OSs bring. I'm talking about different layers here, like the basic computer layer, and then the OS layer, and the layers that we've been playing around in. The OS itself is made up of different layers too. You can like dig down into those, and the user interface is on one layer, process scheduling is on a different layer. To operate the system or hardware, yes, for sure. So common folk can use computers. That's also true. So the way I like to think about operating systems, and all these things are true, but since I tend to think in a lower level way, I sort of ignore the user interface, which is wrong. User interface can be considered to be part of the operating system. But I consider the operating system to be the software that hides the hardware from us. So somewhere we have to deal with hardware, and hardware has its own funky interfaces, and all these different vendors produce different pieces of hardware that have different ways of controlling them. And sometimes we don't want to think about that. We just want to print hello world on the screen. And we don't want to have to worry about pixels, and we don't want to worry about fonts, and we don't want to worry about the exact little specific commands we have to send to that exact piece of hardware that was designed by who knows who. We don't want to think about any of that. We want the operating system to do that for us. So when I say I want to open a file and I want to write some data to that file, I want the operating system to know everything about managing those files. I want it to know everything about how to talk to a hard disk or an SSD. I don't even want to know if it's an SSD or a hard disk. I don't care. I just want to write something to a file. It could be a hard disk. It could be like some kind of weird water-based memory storage that I am unaware of. It could be anything. I just want the operating system to deal with those details. And so the operating system is excellent at that. When we write stuff to files, we don't have to think about how do we control a hard disk. Back in the floppy drive days, those drives were incredibly dumb and had to be micromanaged. The operating system would like send a command to it to spin up the motor, and then the operating system would wait like, you know, a couple hundred milliseconds for the motor to spin up, and then it would send commands like, oh, hey, go seek out this track. And it was, if we didn't have the operating system doing that stuff for us, we, the programmers, would have to know exactly how to interface with all this hardware, and it would be a royal pain. If the operating system weren't in place, we would have to interface with the hardware ourselves in the programs that we wrote, and we would hate it. There is a piece of software that often comes with a piece of hardware that the operating system uses to talk to that hardware. Does anybody know what those pieces of software are called? Drivers. Totally. If you ever bought an off-the-shelf component, probably come with like a CD that says, here's the driver for this thing. And then you probably threw the CD away because the driver was already included with Windows or something like that. But when you manufacture a piece of hardware, like let's say I decide that I'm going to write Beej's remote outdoor thermometer sensor thing, and you'll be able to plug that into your computer and get temperature readings. If it's not some kind of standard USB thing that I've made up, it's going to need a driver. Like it's going to need, the operating system is not going to know how to talk to it because Microsoft doesn't know about the special thermometer gadget that I built. They're not going to write a driver for it. So me as the manufacturer of the piece of hardware, I write a driver for it that works with Windows. And then when I distribute the piece of hardware, I give the driver out along with it. So I'm like, if you want to run this, install this driver so that the operating system knows how to talk to my piece of hardware. So the operating system and drivers kind of go hand in hand. We as normal programmers, we don't talk to the drivers directly. We talk to the operating system, and then the operating system talks to the driver to actually talk to the hardware itself. That's a lot of talking. How does everybody feel about that? About the operating system's place in the world, separating us from the hardware, allowing us to do things like read and write files and put stuff on the screen. Cool. Remind me later, I'll drop you a link to, there's a great repo out there called How to Write an Operating System from Scratch. And it's more than I've ever been through, but it actually only takes about 15 minutes to go through the first several steps to boot up an emulator, a PC emulator, and have it print Hello World on the screen. It's like this little Hello World operating system. Doesn't do anything except print Hello World. But from scratch, you have written a thing that you could boot. And then from there, all you have to do is build the rest of it. All right, let's see here. I want to talk about how to talk to the operating system directly. Get a list of these things. All right. So before, when you're doing stuff with like Node and you write console.log to print something out to the screen, something appears on the screen, right? You haven't actually talked to the operating system directly. Like, who knows what the operating system does deep down for writing stuff out to the screen. You just said console.log and it went, and that was great. All that stuff's been hidden away from you. So the operating system is actually printing something to the screen there. It's just you've called console.log is called something else, that's called something else. Eventually, it talks to the operating system and says, hey, print this out on the screen for me, will you? And that final call, the one that says directly to the operating system that, hey, you should print that to the screen, we call that a system call. That's differentiated from library functions. So library functions are things that exist out in what we call user space as opposed to kernel space. I wish I had a good diagram of this. Let me just make one up. Let's see here. I don't know where this is. That's fine. Some scratch paper. All right, so we've got these two spaces, and I'm going to separate them here. We're going to call this one user space, and this one kernel space. Oops. What is the kernel? Why is it spelled that way? I don't actually know why it's spelled that way. Wikipedia page probably says. I'm going to put in parentheses out here, operating system. Yeah, you've heard of kernel panic. Weirdly, so kernel spelled with an A, the way you just spelled it there, that's the way they spelled it on the Commodore 64. I don't think anybody else spelled it that way. Oh, that's one way of thinking of it. I've definitely seen diagrams that show the kernel inside the shell, like an onion skin thing. The kernel is the core of the operating system. So I mentioned before the operating system has a bunch of layers, like user interface stuff and drivers. The kernel is the bit of the operating system that, is this too simplistic? Can I say this? Seems like it's the bit of the operating system that is not the drivers and not the user interface. It's a bit of the operating system that provides core functionality, and we'll talk about what that core functionality is in a minute. The kernel can talk to drivers, but the kernel doesn't have information about how a specific device works. It leaves that to the driver. When we go between these two spaces, we call this a context switch. When we go from one of these to the other one. A little bit of terminology there. But I'm still talking I'm hand waving here. You guys are like, what are you talking about, Beach? This is fine, we'll get there in a second. So kernel space, kernel mode, when the operating system is in here, it has a lot of power. It can do anything to the system. I should say it has a lot of authority, maybe. So you as a user, if you try to go blow away your whole hard disk, it's going to stop you. The operating system is going to stop you. It's going to be like, hey, you're logged in as user Beej. You don't have permission to delete these files. So no. But the kernel can do anything. It can write anything to anything. It can do anything. It can crash the computer. It can. It's no longer in a space that's managed in a kind of per user sense. Is sudo, is it user space or kernel space? So sudo, the program itself, that program runs in user space, but it makes calls into the operating system. So hold on to that thought, and we'll talk about how to actually get into how to make this context switch and get out of here. So a lot of functions stay in user space. They aren't system calls. So things like printf. This is a function that exists in user space, but eventually if it puts something out to the screen, that's going to come out. That has to go to the operating system because you can't write stuff to the screen without going to the operating system. Other functions that are out here, like what else have we used? Have we used, I mentioned this one, string to unsigned long. This converts a string to a number, just like we did in that sample code yesterday. There's no reason to talk to the operating system at all for this. So the operating system, not involved in this. For printf, the OS needs to output to screen. So the operating system does do something for printf eventually, although the printf call itself exists in user space. It's kind of funky. We can do I'll implement a little printf, and then we'll see the system call happen exactly. Scanf you used this morning, that will also eventually call into the kernel. But let's use printf as an example here. So printf needs to do a variety of things. It needs to look at your arguments. Like, let's say we're printing with %d, we got to print a number out. So it has to look at this value that it has stored as a integer, and it needs to convert that, the reverse of what we did yesterday. It needs to convert it into a series of digits that can be printed out on the screen. So that all happens in user space. But eventually, when the digit has to get printed, printf calls another function. It calls something called write. And write is a system call. This, when you call write, it will cause a context switch to occur, and things will start to happen inside the kernel. So this will do whatever it has to do. Maybe it prints it out to the screen, but if you're familiar with Bash, you know you could redirect output into files, so maybe it's saving it to a file instead, and so on. malloc I love as an example. Malloc starts off in user space, and it actually makes a call. Let's put it out here. Malloc ends up calling something, I think it's called sbreak. I can't remember. And then sbreak is another system call. And we can look these up in our list of system calls that I have here that I just Googled for. So I mentioned write. Let's see, PCI config write, pwrite, blah, 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 blah. Right, there it is. So we have a syscall write that writes to a file descriptor, whatever that is. But look, it takes a buffer and it takes a number of bytes to write. This is a kind of a low-level thing. It's a very basic function that can generally output information, not just strings. You notice this buffer is a void pointer. This thing can just write a sequence of bytes out. So it's general purpose. Printf is a little more specialized and a little more human-friendly. It can do things like print numbers. But deep down, it calls write that talks to the operating system And it's kind of a dumb function. Like, well, it's just going to print out a sequence of bytes, that's all. So write is a little bit painful to use. So printf was invented to make it easier to use. Is it safe to say at any time we need the hardware, we'll eventually make a syscall? Yes, that is safe to say. That is totally correct. So there are a lot of syscalls here. All kinds of stuff that does all kinds of stuff. And you're not expected to know all these, of course. But what all these calls have in common is they are talking directly to the operating system. And when you make one of these calls, a context switch will occur and the operating system will take over effectively. Every keystroke, yeah. We'll talk about this a little bit more when we get to the lower level stuff in computer architecture, but yeah, basically every time you hit a key, the CPU gets alerted that something has happened that needs attention. And some piece of software needs to give that attention. That piece of software is the operating system. And so you press a key, the operating system gets notified that a key was pressed. And in the most simple case, imagine a single processor machine, the operating system is going to stop whatever it's doing. So it was busy computing pi for you or whatever you ask it to do. The operating system is going to be like, hold that thought. We'll come back to you later, but somebody pressed a key and I need to go figure out what to do with that. And so the operating system saves its work, goes, looks to see what key was pressed, handles that, delivering that data to whatever process needs to be delivered to. And then it returns to computing pi where it left off. It's pretty nuts, the number of things that your operating system is juggling right now. We'll talk more about processes in the next hour. Actually, maybe I'll talk more about processes now, and then we'll code up some stuff. It's not just every keystroke, but it's every time one of your programs asks to write something to disk or to the screen. It's any time, like if you ask to read something from the disk isn't going to be ready for that. The disk takes ages to get your information back to you. So you can ask the operating system, hey, will you read this from this disk file for me? And the operating system will be like, sure, I'll get back to you when that's done. Can you skip talking to the OS and just command the driver? I'm not aware of any such circumstance in Unix, and I admit that I'm not quite in my area of expertise there. There's a system call called ioctl IO control. This system call gives generic access to devices or to device drivers. You see, it's just the description: controlled device. Totally generic. So this is a system call that you can use to send basically arbitrary commands to device drivers. And it doesn't even dictate what it is. Its second argument is a device-dependent request code. The third argument is the untyped pointer to memory. So you can just pass this thing arbitrary information and use it to send commands to a driver. But ioctl is a syscall, so you are talking to the operating system when you call it. But yeah, this one system call that people don't use that frequently. This is the window into your average device driver, your average generic device driver. Oh, and we're not going to use that one. mmap, mount, memory unlock, pipe. Has anybody ever used a pipe in Bash? To pipe the output of one command into the input of another command? So deep down, that's making use of this pipe system call. Pip freeze? I don't know what that is. I've never used pip in that way. Pipe freeze. You mean like wintertime? Yeah, that's why we call it the pipe symbol. Anyway, I digress. What else can we talk about here? So we've talked about how we actually talk directly to the operating system by making system calls. And a lot of the times those system calls are hidden away from us, wrapped up in other calls, like printf wraps up a write system call for us. Because we saw write was too dumb to do things like print out numbers for us. And nobody wants to write the algorithm to print out a number every time you want to print out a number. So some enterprising people, when they put this C programming language together, wrote printf to save us the pain of needing to write numbers out a character at a time. Printf then calls write. Likewise, there's a user space memory management system called malloc that comes with the C language. But deep down, the operating system is the one that's controlling access to all of memory. So malloc has to call sbreak. There's break and there's sbreak. I always get them confused. Maybe there's only break. All right, sbreak is wrong. Change the data segment size. So this changes the amount. Oh, sbreak adds to it. There it is. It does exist. It adds the amount of data space, adds to the amount of data space that a process has available to it. And that's nice, but it's not as flexible as, oh, hey, just give me some space and return a pointer to it. And then be able to realloc, stuff like that. That's like higher level functionality realloc is that has been implemented in the C library. But deep down, it's going to call break or sbreak to get more memory from the operating system, because the operating system's controlling all that. You as a normal user can't just say, hey, I'm taking all this memory in the system. The operating system is busy organizing that, controlling who has access to what. Unix-like operating systems are multi-user. So if multiple people are logged in or multiple people have accounts, the operating system is enforcing the fact that you can't look at the data in memory that's owned by another user. You can't look at data on the disk that's owned by another user. The operating system is enforcing all that user stuff. Oh, this looks like a cool little diagram. No, really, zoom in. There we go. Weird. Yeah. Memory management, process management, virtual file systems, networking. IPC is inter-process communication. Here's our system call interface at the top. Here's our applications, our libraries, and so on. So here's user space, here's kernel space. I like this diagram. Good stuff. I should steal it. Later when we get to architecture, we'll talk about the stuff down here at the bottom. My favorite. Okay. Let's do a little demo program. Let's write some code here. I was going to talk about processes next, but But I think maybe let's drive home some system call stuff. Well, let's write our own little version of printf. It's going to be kind of dumb. It's just going to print strings out. That's all. Let's go in here, and do I already have a C directory? I do. Oh yeah, we were looking at assembly code last time. We'll write a program called print string, and we will make this work. This one's going to be pretty straightforward. So print string is going to take a string, and it's going to return nothing. And we want to output that string just to the console. I already hinted that write is probably the way to do it. So we'll use that and try to sort something out with write. I want to talk about three things before we write this, though. Standard input, standard output, and standard error. Does that ring a bell for anybody? Sometimes written as STDIN, STDOUT. Yeah, I've got to definitely bring something in. We'll get there in a second. So in Unix world, there's a saying that everything is a file, and it's not actually technically true, but a lot of the stuff you do gets used through a file type of interface. And we're used to reading and writing from files, but here, the console, when you put something out to the screen, that's also a file in Unix world. Whenever you launch a process in a Unix-like operating system, 3 files are set up for you automatically: standard input, standard output, and standard error. And those files have numbers associated with them called file descriptors. So file descriptor and the file name, file descriptor. So file descriptor is just a number. Number 0 is standard input. File descriptor number 1, standard output. And file descriptor number 2 is standard error, we call it. So these file descriptors are set up for us automatically whenever a process is created. So our process that's going to run right here, it's going to have these 3 file descriptors set up for us. Standard input is typically the keyboard, but can be changed. Standard output is typically the screen, but can be changed. And standard error is also typically the screen, and also can be changed. So if we want to write something to the screen, we want to write it to file descriptor number 1, standard output. But let's have a look at the write system call and see what that's like. Let's see, this was there, and write was way down at the bottom. Write to a file descriptor. We got to include the Unix standard header file. So we'll take that. Actually, I'm just going to copy this whole thing so we have it for reference. I'll add a note here. Usually the screen. Oops, sorry. This is usually the screen. This is usually the screen. And this is usually the keyboard. Okay, so I'm bringing this in. This is our write system call. So we got to pass some stuff into it. It returns an S size T, whatever that is. The man page would tell us that this is the number of bytes we actually wrote out. It may be fewer than the number of bytes we asked for. So if I were doing this correctly, we'd write a loop and make sure that we were getting all of our bytes outputted. But I'm just going to assume we're going to get them all done in one go here. Hello world isn't that many bytes. So the first thing is the file descriptor. And we want to output to the screen, which is standard output, which is file descriptor number 1. And then we need a buffer. The buffer is a void pointer, so it's a pointer to any kind of data. This is what we want to write out, the sequence of bytes. And I want to write S out. And then count is the number of bytes that we actually want to write. What is that going to be? How many bytes are we going to want to write to print out our string? How can we figure that out? Size of, yeah, or something. You're on the right track. We can't use size of here because size of a char pointer is like 8, always, because it's just a pointer variable, just like the size of an int is always 8. We want to figure out the length of the string, though. Size of would work if the string were an array, but it's not. We want to use Sterling. Yeah, that comes from string.h. Whoa. So we're going to figure out the number of bytes in the string. We're just going to pass that in directly. Sterling of S. So we passed in 3 things. The file descriptor, we use file descriptor 1, which is always standard output. And the buffer was the string we wanted to print, and then the count was the number of bytes that we wanted to actually output. We've included Unix standard.h to get our write system call. And then we're going to call our print string to make that happen. The second we call write, our program stops running and the operating system starts running. The kernel starts running at that point. So this is a little bit of a weird thing to think about, and it makes it easier in my mind if you think about it as if you were on a single core machine. You only had one processor. The one processor on your machine can only do one thing at once. I mean, it's like a little machine. You can't ask your car to drive 2 places at the same time. You can't ask the CPU to do 2 things at the same time. You can only have it do one thing, assuming it's a 1-core processor. So our program's going to be running here. It's going to be like, okay, we're in main, we're calling print stir, we passed all these variables, blah, blah, blah. And then as soon as write happens, the operating system gets called and our program stops running. The operating system starts running, and it's been passed this data right here, everything it needs to know in order to get its work done. It's like, oh, I've got file descriptor 1. I know what that is for this process. The operating system is managing what the file descriptor is for the process. So it knows that 1 is going to the screen, or maybe it knows that 1 is going somewhere else if we've redirected it. It knows what to print and knows how many bytes to do. So this is going to take some time to accomplish. Our process may go to sleep for a little bit. The kernel might be like, okay, you called write, so you're going to go to sleep, and I'm going to take care of this write thing, and when I'm done, I'll wake you back up again. And we'll talk more about that next hour when we talk about how processes work. But the point is, the operating system takes over when we do this. We hand off control to it willingly, and it does the work it has to do before coming back to us. Anyway, let's give this thing a build. If I'm lucky, it'll say hello world. I forgot my new line. How unprofessional. There we go. Now that went to the screen. Some of you may have used this trick in Bash before, the greater than sign, to do redirection. This means when you put this in Bash, this means take what normally would have gone to standard output and send it to a file instead. So Bash is going to set up some, do some machinations before these programs run in order to make sure that standard output from print string doesn't go to the screen. It goes to this file instead. If I hit return, sure enough, it doesn't go to the screen. I have a file now, foo.txt, that's got hello world in it. So there's an example where even though we said, hey, I want you to print to standard output, and standard output's normally the screen, here the shell has done some things, Bash has done some things to make it so that standard output didn't go to the screen. But what's cool is we didn't have to change our program at all. Our program is just like, I'm writing to file descriptor number 1. That's all. So that's kind of cool. Piping works the same way. There's a command called word count that tells you how many, like word count minus W will tell you how many words you have. There, I had 2 words, it says. We could do the same thing. Print stir pipe to word count minus W. Print stir is still sending standard output, but here Bash has set it up so there's a pipe now between standard output and word count. Anyway, a little aside there on standard output and some of the power of the operating system to change where it goes without ever changing our program. So deep down inside printf somewhere, there's a write call that prints stuff out. Of course, there's a ton more code to deal with printing out numbers and floats and pointers and hexadecimal numbers and everything else that printf can do. Left and right justification, field widths. Printf has a lot of power. And our version of printster is kind of lame in comparison. Prints a string and that's all. Anyway, thoughts or questions? The idea here is to be familiar with the fact that we were running in user space for a while here, and then we switched into kernel space by making a system call. The kernel handled that system call for us, and then it returned us back to user space, and we continued executing this program. All of this follows the progression from starting up in JavaScript land and dropping to C, and now we're talking to the operating system directly with system calls, and we'll just kind of follow this rabbit hole over the rest of the program until it gets to the bottom. So could we take a print, could we pass a void pointer and print any data type? So yes, but it's not going to be what you want. Let's do it. So we immediately run into problems because strlen only works on strings. So that's going to be unhappy. In fact, I think we might get some compiler warnings here. Oops, I changed it to P, my mistake. No, it's still happy. Really? Are you still totally happy? You're still totally happy. All right. So now we should be good because void pointer is just like any pointer, and the thing that we're pointing to is a string. So if I run it, we're still happy. But what if we put something else in there? All right, now we've got an integer with value of 12. It takes a void pointer, so pointer to anything. I change A to a pointer to A by using the address of operator here. So here we have a pointer to A. We pass that in. Let's see how this goes. What do I think is going to happen? I think that the output is going to be messy and it won't crash, but maybe it'll crash. And it's not even messy. Hang on, I'm going to pipe this to a program called hex dump so we can see exactly what bytes came out of it. It printed out a 0C and then stopped. 0C I recognize as 12. But basically what it did, we're lucky this worked at all. Basically what it did was take 12 and print that out as a byte. You know, I mean, that's what the write does. It prints a sequence of bytes, right? So 0C is hexadecimal for 12. It printed that out. But in ASCII, that's like some unprintable character. I don't know what 0C actually is. Let's have a look. ASCIItable.com. Hex 0C right here. Form feed. If we were on a printer, this would be a directive to skip to the next page. But it's not something that we can see on the output. Like when we ran it, nothing appeared. And then we got lucky because it was followed in memory by a null because Stirland stopped at 1 byte, which was lucky. I think if I put some more stuff out here, actually, let's change this to char. Now let's see what happens. Still nothing. I'm going to put another char afterwards in memory. Still unexpected. We're kind of messing around in crazy land right now because Stirland is looking for the end of a string and we're not giving him the string. Ha! I got my A to print out. So this is insanity, right? What did I just do? I just added a character up here, B, an unused variable. And then when I run it, we see the B. Ah! What manner of sorcery is this? We're basically engaging in undefined behavior at this point. So by calling Stirland on a thing that's not a string, we got a pointer to an unsigned char here, but then we just gave it a value of 12. We're getting into some weird space. And so Stirland goes through memory a byte at a time looking for a null character to dictate what the end of the string is, but I don't have a null character here anywhere. I've got a 12 that's unprintable, and then I've got a letter B that does print, and then afterwards in memory there's a null. We just got lucky, and there was a null there, but there certainly didn't have to be. Yeah. So the short answer is it's not going to do what you want to print any data type. If you want to print out a number, you're going to have to take that number, You're going to have to mod it with 10 to see what the lowest digit is. And then you're going to have to divide it by 10 to get to the next digit and print out each digit one at a time. The reverse of what we did yesterday when we were turning a string into a number. So we would have to do it the hard way. Taking the strlen of something that's not a string definitely gets us into trouble. Let's undo that. Back to sane world. Okay. I do want to talk about processes next, because a lot of the stuff that you guys are going to be doing in this lab is process oriented, with making more processes. So I want to talk about that next, but I do want to take a break, and I do want to answer any last minute questions about kernel space versus user space, calling into the operating system with syscalls, anything along these lines before we start talking about processes. And if you need something to do during break, come up with that algorithm for printing out a number. Ooh. There is a version you could write. I'm going to call it print num. It'll be a challenge for you guys. And maybe we make it an unsigned, just to make life a little bit easier, so you don't have to decide if you're putting a minus sign or not. Something goes in here with a right somewhere. I'll leave that as an exercise for you guys if you want to do it. All right, let's take a 5-minute break, and then when we come back, we'll talk about processes, how the operating system manages what processes are running where, and how we make new ones. A whole lot of the lab today will be making new processes. All right, I'll put up a timer here. Everybody run and grab that coffee. I'll catch you in 5. And we're back. Everybody coffeeed up? Coffee. One thing I will point out about these system calls is system calls like write and break and the other ones we've talked about. These system calls tend to be the same, not always, tend to be the same in most Unix-like operating systems. So Android and iOS and Mac OS, they all have a write system call. It all works basically the same way across all of them. Windows being very different, it has its own collection of system calls that are different. Same concept, they're just not called write, called other things. Okay, let's talk processes. This is an important concept in operating system land, and again, basically what we're going to be doing for most of our exercises here with this next day or two. So, what is a process? What have you guys heard? Or where have you heard processes mentioned? In what contexts? The task manager, for sure. That one's pretty direct. It kind of gives you a list of processes that are happening. Anywhere else? Any other process exposure, memory reading? Processes do read memory, and they are limited to the memory they can read. Every time I launch a process, it gets what's called a process ID attached to it. And I can't remember. That's somebody's process ID. I think that's my process ID. I think that's the process ID of this bash shell that I'm running right here. I can get my process ID. There's a system call to do it. Let's have a look. I'm not doing print num here. I'm going to print out my process ID is %d. I'll put a new line here. And there's a system call called getPID. This will ask the operating system, hey, what's my process ID? Yeah, let's just start with that. Oops, I'm using printf now, so we need that. Center IO, center IO. Unused parameter n from print num. Yeah, that's okay. I'll ignore that for the moment. So print stir says my process ID is 62210. I'll run it again. 62213, 62215. So getting generally bigger. Every time I run it, I get a new process ID. Every time we run this, a new process is created. And every time that process exits, that process is destroyed. So what does that even mean? What is a process from an operating system standpoint? The process is the operating system's idea of what an individual running program is. And so we're asking the operating system to run a whole bunch of programs. Right now, they're the obvious ones, like you're running Slack, you're running Zoom, you might have code open, you might have some terminals open, you probably have a browser open, you might have your mail reader open. You've got a number of processes that are obvious to you that are going. But all of those processes actually have a pile of sub-processes that are supporting them as well. So a process might launch and then it might start off on its own. It might start like 10 more processes to deal with various things it needs to do. So there are a lot of processes going. And some of them live longer than others. Like you've probably had Slack open for a while now. That process hasn't gone away. My little print stir process, it launches, does its work, and dies immediately. And so there we had process 62256. It lived for a fraction of a second, and then it went away. But you can see a lot of processes like that were happening because the last time we ran it, it was 62244. So 12 processes came and went in between our creating another print stir process. The operating system is juggling all this stuff all the time. Processes coming to life, going away. It's managing which one gets to run at any particular time. We call this the scheduler. The operating system decides what process gets to go. Remember my simplistic example where I said, let's say we only have one CPU. CPU could only do one thing at a time. But if we have 10 processes that we want to be responsive from a user perspective, the CPU has to run all 10 of those in a kind of pretend simultaneous way. If you can only do one thing at once, though, what do? How does a single CPU make it look like multiple things are happening at the same time? Any ideas? Or as a hint, let's say you as a human are only good at doing one thing at once. How do you make it seem like you do multiple things throughout the day? Switching tasks quickly. Context switches are involved in switching tasks quickly. So yeah, if you can only do one thing at once, but you jump back and forth between doing two things really quickly, even though you're only doing one thing at once here, and then another thing here, another thing here, another thing here, if you do that quickly enough, then you can fool your human overlords and make it look like you're doing two things at the same time. Because humans are pretty slow, and we don't notice 20 milliseconds here, 20 milliseconds there. So they call that time sharing in an operating system context. So the OS is going to bounce back and forth between a whole bunch of different processes, giving each one a little bit of CPU time. It's like, okay, Zoom, you can do what you need to do, and I'm going to give you 10 milliseconds, so go. And Zoom's like, crunches away for 10 milliseconds, and then the CPU is like, stop. It actually interrupts what Zoom is doing, and then the CPU looks at the big list of processes it has to deal with. It's like, okay, my user is asking me to run 200 things. Which of these needs to run right now to get the best user experience? And so it chooses out of all the processes. It's like, okay, this one hasn't run in a while. I need to get on that. You've got 10 milliseconds. Do your thing. And that process crunches away, and then the operating system stops it and chooses another one. And the operating system, we call this scheduling. The operating system is scheduling processes to run. And there are different kinds of schedulers. But the general idea is that we want the scheduler to choose processes to run in such a way that the system feels responsive to us. At least in a user-centric environment. On my Mac, I want my Mac to respond to me. I don't want it to sit around for 4 seconds ignoring my input while it's busy doing something else. So the scheduler on a Mac is tuned so that it's responsive to user input. On other things, maybe the tuning is different. Like maybe you have an operating system that's dealing with maybe inputs from an automobile subsystems, and the computer has to make instant split-second decisions, life or death decisions about how to control the automobile. And so maybe it's a little bit different. Maybe it's like, you know what? I'm not going to update the little screen that the user has on the console. I'm going to hold that off for 200 milliseconds because I need to do this really delicate maneuver to keep the car from spinning out of control. So maybe the scheduler in a car computer has different priorities. Maybe it's more interested in giving the car subsystems time than it is in giving feedback to the user through some screen on the dash. So the scheduler can be tuned to make decisions like that. How many processes do you think I have running on this computer right now? Place your bets. Make a guess. How many processes? Then we'll average them and see how close we are to the real number. 250, 150, 65,000, 320, 200 plus. There is a command you can run on the console here, PSAUX. This will list all the processes you have running on the system. One per line. So all kinds of stuff. I'm going to go ahead and pipe that to word count minus L for lines so we can see how many lines there were. And this should give us roughly how many processes we had at that instant in time. Of course, as we see, processes are coming and going all the time. So this is just sort of a quick snapshot. What do we got? Oh, piping doesn't work correctly on this Mac for some reason that I never figured out. At least not from PS. I think that's the actual answer, though. So around that many. So those were all good order of magnitude guesses. Although 65,000 is probably pretty close to the maximum number of processes that's allowable. I don't know how high process IDs go to. Sometimes it only goes up to 65,536 for wrapping back around. So if I only had one CPU, the operating system would have to be juggling all these things, all 150 of my processes to try to decide which one's going next. Fortunately, only a few of these processes are demanding attention right now. So I've got a bunch of tabs open in Chrome. There's probably one process for each of those tabs, but most of them aren't doing anything. They're just sitting there. The process still exists, but it is what we call asleep. And in fact, this column in the output right here with all these S's in it, this is the process status. All these processes are asleep. So virtually everything is asleep here. Let's see, I think if I run htop, no, this gives us a better number. We should have done this. You might not have htop installed, but you probably have top installed for something similar. So this says we've got 482 tasks. I don't know what this number is. 7 of them are running. 3 of them are running. 1 of them is running. So we've got 481 tasks here in this giant list, but only a handful of them are demanding attention of the CPU. The rest of them are asleep waiting for stuff. So we can control our process, and we can ask the operating system to make new processes for us. That's sort of the level of control that we have. And I'll do a demo program of that in just a second. We can see what processes are on the system, at least to the extent that our user permissions allow. But we can't exactly dive into them. These processes are isolated from one another, certainly on a user sense. Like if you were a different user than Beej on this system, you could not look at memory that was being used by my processes. That would be a security risk. But even in general, processes can't look into the memory of a different process. You have to set up some special stuff to make that happen. The processes are pretty well isolated from one another. But we can ask the operating system to make new ones for us. And in fact, that's how bash works. When you run a command, bash says, hey, operating system, make a new process so I can run this thing. Like bash doesn't go away after that process runs, right? The bash process is still going. It's still there. But bash asks the OS to make a new process so that it can run commands on your behalf. So the administrator's account, yeah. So if you're logged in as root, you have a lot of access. Yeah, so root can do all kinds of stuff. Usually operating systems expose all of main memory in a special device file somewhere. So you could just go open that if you were root and look through memory and extract blocks of memory from any process. So the root account is pretty powerful in that regard. That said, it's still the operating system that's enforcing that. And there are a couple things root cannot do, actually. If you Google for things that root cannot do, you'll end up with a list of, like, you can't unmount a busy file system or things like that. I can't remember. The current view, yeah, let's consider tasks and processes to be the same. I'm not sure why it's called tasks there. Let's run regular top and see what it says. Not regular top just calls them processes. 481 total, 9 running. 1 was stuck. I don't know what stuck state is. 475 of them are sleeping. And then we've got a bunch of threads. I'm not going to talk about threads yet. I can sort this thing. Let's see here. Oh, maybe not this version of top. Hang on a second. Can't remember how to use these. Let's see, sort by percentage of CPU. There we go. All right. So now we're sorting by CPU percentage. So we see that Zoom is using 127% of my CPU, which seems like an excessive amount. We'll talk more about that in a second. And then we've got these other little things running. User SBIN dist noted. I don't have any idea what that is. It's using 10% of a CPU, 10% of my CPU. Slack is using 5%. Other miscellaneous stuff. HTOP, well, the program that's running right here before us, using 0.2%. And this percentage is a measurement of kind of like the time that's being used every time slice. Like top doesn't need that much time to get stuff done, so clearly it doesn't use that much. But Zoom is busy encoding video and transmitting data and doing all kinds of stuff that needs a lot of CPU. The reason it's more than 100% here is because I've got 4 CPUs in this computer. They're listed up there at the top, 1, 2, 3, and 4, and their amount of utilization is shown. So Zoom is using more than 1 CPU, basically, is what we have here. Which is kind of expected. I'm asking it to do a lot of stuff, so it's probably got multiple processes doing multiple things. Anyway, any questions on this concept before we actually write some code that makes new processes? The fact that the OS is managing all these processes that exist, and it's deciding which one's going to run next on multiple core machines or multi-processor machines like this one. It allocates processes between the different cores, so it decides, it's like, oh, I've got core number 3 is idle. Let's put a process there to run it on that core, that kind of thing. This command was something called htop, and you probably have to install that. I think I got it from Brew. The stock one is just called top. I'll give you 2 answers to that, Raymond. Is there a lot of work behind killing a process? So from a user standpoint, no. It's just one system call. That's it. You can kill a process off, assuming you have permission to do it. You can't kill other people's processes unless you're root. But you can kill your own processes. It's a one-liner. That said, there is some maintenance the operating system has to do. There's overhead there, but not enough to really stop you. If you think about it from what the OS has to do from a process standpoint, it has to keep track of the memory that's associated with the process. It has to keep track of all those file descriptors like standard input, standard output, standard error, and any other files that it's open. It's got to keep track of all that stuff. Did I already say memory? I can't remember. It's got to keep track of the code, like where the code is in memory. So it has to, for every process you create, it has to do some bookkeeping to keep track of all that stuff so that it knows enough to be able to schedule it later. And kind of the reverse bookkeeping has to happen when you kill that process off. There's a big table called the process table that the operating system manages, the kernel manages this. And when you launch a new process, that process gets added to that table. When you kill a process, it gets removed from it. But this is a pretty fast thing to do, so don't be afraid of killing a process. I can do a quick demo from the command line of killing a process. This isn't going to be in C. This is going to be a bash thing. But actually, what is the best way to do this? All right, let me see if I can make this work. Quick test, first of all. Boo! Exclamation point has special meaning. All right. So I've just made this little mini program here that sleeps for a number of seconds and then prints out a letter, prints out hi. So I'm going to have it sleep for 60 seconds, a full minute, give me plenty of time. And then I'm going to run this in the background. If you put an ampersand in bash after your command, it'll run that thing in the background instead of running it in the foreground. So it'll give me a prompt back right away. It'll continue running sleep 60 in the background, and eventually we'll print out hi. And what bash has told me right here is, hey, I just started a process for you, process 62450. It's running in the background right now. Right now it's sleeping. It's going to sleep for another 50 seconds, and then we'll see the letter, the word hi appear. But I'm going to kill it. I'm going to kill process number 62450. And that's that. So that process has now been removed from the process table. It never finished. We just killed it outright. Bash got a notification, which is why it told us right now, oh, hey, I just terminated that, by the way, or that was terminated. So killing a process is that easy. And if you wonder how the kill command worked from the command line, it just calls the kill system call, which you can call right from C. You give it a process ID, and you give it the signal with which to kill it, something we haven't talked about, but even there are many ways to kill a process. Processes can actually override this. So the process might be like, oh, you wanted me to die? No. And it can override it and not get killed. Although there is one signal that it cannot override that will definitely kill it. The ID and port number are different. Yes, those are different spaces. Different spaces entirely. Port number is all about networking. And when we talk about web servers in an upcoming sprint, I think maybe, we'll talk about port numbers, how that works. But let's make some processes. Let's make this happen, because this is about what the whole project is about for the next couple days. It's going to be similar to what I'll code up right now. I'm going to make a new file. We're going to call it proc.c for process. And what should we do here? I think what I want to do is maybe make a couple processes and then wait for them to complete, maybe something like that. Let's do that. well, we'll start off more simply. We'll just make one process. So of course we have this, I'm going to call this the parent process. We already have a process made for us when we run a program like this. Whoa, that was some interesting completion. And I know I'm going to need this. It seemed like, no, let's see. I'll need that eventually. So that's straightforward enough. We haven't done anything weird, right? A process got created. Let's print out our PID right here. So just like before, process got created. It's got a process ID, but let's make a child process. So let's create a new process. So our process is running here. It's run a printf statement. It's run a get PID system call, but let's make a new process right here on the spot. And there's a system call to make that happen. It's called fork. This creates a new process. And the way it works is pretty funky compared to everything that you've ever done before with functions. So at this point, so right now there's one process that exists. Right after this, there will be two processes, the parent and the child. Let's give this a run and see what happens. It printed it twice. Why? I'm going to add some more code here while you guys are guessing why it printed twice. The original and the forked. Yeah, I'm going to name them the parent and the child. Let's print out some PIDs here. So I'm the parent process. My PID is blah, 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 38. And then we got our what printed out with 38 and process ID 39. So there are two processes. So fork has let our original process keep going, the parent process, and it's created another one, the child process. Watch this craziness. Never do this, by the way. Anybody want to guess how many this is going to print out? All kinds of stuff. 8. 9. Is it 9? I think it's 9. So what happened? We got the parent, it made a child, and then the parent and the child both made 2 more, and then all 4 of those made 2 more. So I think it's 8 plus the parent. Is that how that worked out? I'm not sure. 8 is what I would have guessed. So we had 1 make 2, and then each of those 2 made 2 more, and each of those 2 made 2 more. So you can make processes really quickly. What you don't want to do ever is something like this. Like, seriously, don't do that. Your system will just basically hang instantly, and you'll probably have to hard power it off, because this will make a bazillion processes in no time. Like, sure, the first one will just make one more, but then it'll make 2 more, 4 more, 8 more, 16 more. It only takes 15 steps before we've got 32,000 processes created. Yeah, so we call this thing a fork bomb. I think there's even a Wikipedia article on fork bombing. So whenever you have fork in a loop, be extra, extra careful that you're not very rapidly making processes without having them die off. There's definitely a place to put fork in a loop, like most servers do, but they're very careful to not have too many things going crazy. So back to our original example here. It seems marginally useful, right? I mean, we launched this other process and they both did the same thing afterwards. They both printed out what and then exited. Like, what use is the child process if it's just going to do the same thing that the parent process was going to do, just twice as much of it? That doesn't seem very useful. What we need is a way to differentiate between the child process and the parent process. We need to execute some code if the child process happens and some different code if the parent process happens. And it turns out fork gives us a clever and counterintuitive way of doing that. Shown fork. Here we go. Fork system call. And it has to do with the return value. So we're ignoring the return value, but it returns a PIDT, which is a process ID. It's just a number, like we've seen, our big process ID numbers. So how is that useful? Let's look at return value. Return value. On success, the PID of the child process is returned to the parent. At 0 is returned to the child. So fork returns a different value depending on whether or not you're the child or the parent process. This is how you can differentiate the two. So it returns 0 if we're the child, it returns the process ID if we're the parent. So I'm going to get that PID right here. I'll declare a new variable PID of type PID type, and I'll call fork and see what happens. And it says that if it's the parent process, it returns the PID of the child. So, and it says it's 0 if it's the child. Let's start with 0. So if the PID is 0, then we're the child process. The child process ID is not 0, actually. It has a process ID that's some number. It's just that 0 has been returned by fork so that we can tell that we're the child. Ooh, child process. If it's 0, there is actually a -1 case. I'm ignoring it. Fork will return -1 if there's some kind of error, like the process table's full or something like that, or you're out of memory. But I'm ignoring that right now. Otherwise, we're the parent. I'm the parent again. Our PID is still this number. I'm going to leave this what in here for now. But this is how we differentiate. Oh, let's see. If PID was not 0, actually, let's print that out. I'm going to print out the PID that we got back from fork. So what do we have here? Typical parent process thing. We fork a new process. We check the return value. If it's 0, we must be the child. And we can print out our own process ID by calling get PID. Otherwise, if it's non-0, it's the parent process. And the return value is the process of the child that we just, or the process ID of the child we just made. What's super weird is that fork is returning one thing to one of the processes and a different thing to the other process. Does that weird anybody else out, or is it just me? We're used to a function returning a thing, and that's it. But here we have this weird case where one process gets one return value and another process gets a different one. So the PID variable, you mean? Did I misspeak earlier? So the PID variable is definitely 0, but the actual process ID is some number. Well, here, let's run it. And I'm not sure I'm answering the question, though. So first line, process ID of the parent ends in 29. And then the parent is still running. It says, I just spawned process number 62630. And then looks like this is the parent still, prints out what, and then it exits. And then the child process gets its turn to run. Notice that they're not running at exactly the same time. The parent process ran for a while, and then the child process started running. So it says, oh, I'm the child process, 62630. That's this line right here after the fork. And then the child process continues to run. It runs here and it prints out what, and then exits. So we got that print out here. The scheduler has decided, in this case, the parent process is going to run all the way through, and then the child process gets a chance. If we run it repeatedly, that may always be the case, or it might change up. Oh, I saw it. Where did it change up? Yeah, right here. Here, the scheduler scheduled it differently for whatever reason. So the parent process printed out this first line, and then the child process got to run. And I don't know why it happened in that order. The scheduler, maybe it had free space on one of the other CPU cores and decided to run it there. We cannot guarantee the order that these things run in. Well, actually, we can. We could add more code to make that happen. But how's everybody feeling? The trickiest part here is that return value from fork. But it's really useful in my mind if you remember that when the fork occurs, two processes now exist. And because two processes exist, there's no reason why fork can't return one value to one of them and return a different value to the other one. Fork's also a system call. So like all system calls, our program starts running through main, prints this out, it gets to the fork system call, and the operating system takes over. At that point, our process stops running for a second, operating system takes over, says, oh, you're asking me to make a new process. Okay, we're going to do all this bookkeeping I have to do. Bam, I got two new processes. And then it schedules one of them to run, schedules the parent to keep running, or it schedules the child to keep running, however it decides. And then one of those processes continues to go back here, back into user space. I don't know, thumbs up, thumbs down? Is this cool stuff, or is it just weird? You guys probably wouldn't believe how close we are to writing a bash clone right now. It's actually, we're not far off. There are only like 3 system calls you need to write a bash clone. All bash does is launch new processes and wait for them to finish. Well, So there's two processes, even though there's only one set of code, lines 8 to 14. That's correct. There are two processes concurrently executing through that code. And doing this if test to see if the PID is 0 or not. That's how we decide, oh, hey, the child's going to run this block of code. The parent's going to run this block of code. I guess another thing I could add here is that as soon as you fork a new process, both processes get their own copies of all the data. So there's not just one PID variable here. As soon as we fork, there are two PID variables, one for one process, one for the other process, and they're totally independent. One of the processes could change that value, the other process wouldn't know because their copy doesn't change. So as soon as you fork a process, you get a total copy of all the data that exists in that process. And so changes to variables the child makes are not reflected in the parent and vice versa, because they all have their own independent copies. And you might think that sounds inefficient to make a whole copy of the entire thing, but there are cool features of modern processors that actually make it quite efficient to do this. So when the code is running, is the code itself the parent or the child or something else? You mean like how would I describe this? I tend to think of it as a process running some stretch of code. So you've got in memory, you've got like chunks of code that can be run, and processes make their way through that stretch of code. And maybe two processes run the same piece of code, or maybe they run slightly different pieces of code. Like we saw earlier, it was printing out what twice, well, it still is, right? Because both the parent and the child process run this exact same line of code when they get here. So I separate the process, the concept of the process in my head from the concept of the code. So you could have one copy of the code with multiple processes executing that copy of the code. Does that kind of answer your question? Cool. I realize I'm going over now, so if you have to split for lunch, go for it, and I'll just keep recording this thing. But I want to demo one more pattern here that's going to come up in the exercises, and that has to do with exiting processes. So this pattern we have here, it's kind of weird because both processes fall out and execute this what line at the end. But a more typical pattern is you launch a child process, it does some stuff, and then it exits without continuing on the program. So I'm going to put that here. I'm going to put an exit 0. And this is going to cause the process to exit. If this were the parent process, it would also exit. But I'm just going to have the child. So basically what's going to happen, we're going to fork the child. The child will see that its PID return from fork is 0. So it's going to start executing this code. It's going to print out its PID, and then it's going to exit. Process will end. It's like the process is killed, but the process is just saying, no, I'm done. So scheduler, you don't have to schedule me anymore. So if I put this exit line in here, I may have to, yeah, exit's actually weirdly in standard lib. .h. So the second what should not show up exactly. The child process will run printf, then it'll exit and it'll be done. Meanwhile, the parent process will come down here, run printf saying it's the parent, and then the parent process will continue, print out the what there. So there we go. So the parent process 62728 runs. On the parent again, I just spawned 62729, and then the parent prints out what? 62728, and then here's the child process saying 62729. So this is a really common pattern what we have right here. spawn a child process, have it do some work, then have it exit when it's done. There's one more thing I want to show you here. I want to make it so that the parent process waits for the child to finish. So I want the parent process to launch a child, wait for the child to be done, and then the parent process will continue. I'm actually going to kind of simplify this code right now since the child exits right there. I'm going to just take this else out because the child's not going to continue after this point. So this is going to be the parent. Make sure that still works. So we're still happy. But here, like, we see that the parent goes all the way to the end without waiting for the child to finish. But we can enforce that. Like we were talking earlier about, can we enforce the order or not? Typically no, but we can add some additional stuff to sort of make it happen. So I'm going to print out waiting here as the parent, and we're going to wait for the child to finish. And there is a system call to make that happen. Called wait. There are different ones here. There's wait PID. Oh, this isn't actually giving me what I want. Just look it up in the man page. All right, wait and wait PID. These are the ones that I'm interested in. Wait PID allows you to wait for a specific process ID. Wait allows you to wait for any process, any child to exit. So I'm just going to use wait because it's a little bit easier. And then the W status is a way to get information back from the child. So we can pass null in there if we don't care. I'm just going to jump to that. It says this in here somewhere. Wait, so I'm going to call wait null. And what this means is wait for any child process to die. And I don't care what the exit status was. The null means I don't care. So if we do this, now what we should see is some combination of these initial lines, but that the parent should print waiting and should stop right here. Then if the child has not run yet, it's going to run, and then the parent will continue on. So the parent is going to wait for the child process to die. All right, so here we go. On the parent process, I just spawned the child. Now I'm waiting. Then the child process runs, and then the child process exits, and then the parent process continues and prints out what. So wait is a control mechanism that we can use to wait for a process to complete. So it gives us a little bit more control from the parent's perspective. Like, hey, should we continue running yet? Maybe I want to spawn a child process to do a thing, and then when it's done, I want to continue going. So that's what wait is for. Any questions about that, or what's everybody think about this? What's our level of overload? Might be my next question. This is totally hardcore. Yes. We are talking to the OS and we are creating processes to do things for us in the background on the fly. And then we're waiting for those processes to complete. So it's like we're interfacing with the scheduler here in a pretty direct way. Like, hey, make me a new process operating system. Have that process print something out on the screen and then wait around for it to finish. And so the hardest part here is probably going to be juggling in your head, like, I've got multiple processes going. They're both running through the same code, though. So that's weird. What I do in my mind is I imagine a little arrow, like a little arrow next to one of these line numbers, showing me where a particular process is running at any one time. And normally, if you're not making any child processes, then it's easy enough. It goes from line 7 to line 8 to line 9 and so on. And there's just one arrow that's going along your program as it's executing. But the minute you call fork, now we have 2 arrows, and they're both moving independently throughout the code. One of those arrows ends up on line 12 if it's the child process, and ends up on line 16 if it's the parent process. So we've got like 2 arrows. I'm about to point at my screen, but moving along through our code at once. So let's see here. Let's see if I can actually make the arrows. So we start off, the parent process is there. Oh, I'm not using tabs. Tabs would have totally won. So then the parent process moves here. And then we call fork. And then there are 2 processes right here at this line. And the scheduler decides which one of them is going to run. Let's say the parent process runs. So the child stays up there on this line. The parent process goes to here, says, hey, is my process ID 0 or the PID variable 0? No, it's not, because I'm the parent. It gets returned the child PID. So parent doesn't go into there. Parent jumps down to here. And then it prints out, I just spawned this child. And then let's say the scheduler breaks in and says, actually, parent, you're done running for now. I'm going to schedule the child process to run. So this parent process position stays the same. The child process up here comes out of fork. It hits this line and says, is the PID variable 0? It is, because fork returns 0 to the child process. So then the child process steps into here. And then maybe the scheduler decides, oh, hey, wait, let's run the parent again. So the parent starts running, and it goes to this line, and it prints out waiting, and it goes to this line. And then it calls into the operating system and says, hey, I want to wait here until the child finishes. The operating system is like, fine, okay, I can schedule the child. So the operating system comes up here and schedules the child to run again. Child prints out on the child process, and then it exits. And then it's gone. And the scheduler says, was anybody waiting on that? Oh yeah, this process over here was waiting for that child to die. So I better wake it up and say like, oh, hey, yeah, you were waiting for that? That's done. And the parent process is great, it keeps on running. It prints out what, and then returns 0, and it exits. And that's that. The life of the process. So number one thing to remember, don't put a fork inside a while loop today. I'm pretty sure none of the exercises have that, or if they do, make sure there's a wait in there as well. Repo. Everything I didn't give you yesterday is on Training Kit. All the stuff I meant to give you and then I didn't. Let me give you a link to that right now. So this link is going to be for stuff I should have given you yesterday, but I talked about a lot today in lecture, and stuff that you should look at for tomorrow. 1, 2. Oh, wait, where am I? Oh, looks like there are only 2 videos anyway. Is that true? Hang on a second. Make sure I give you the right thing here. Yeah, all right, here we go. So here's TK. And then also there is a GitHub repo for these 2 days, which is right here. So lots of good reading, a couple good videos there, and then let's see, you can just jump into the exercises. And it should be very similar to the stuff that we've done here today. So let me paste this in for you as well. Computer. And I'll also put in, I'll put on our little Prinster thing, even though this is slightly less relevant. Any other questions for me before we do this late lunch? You guys just ready to tear into it? I just looked at that the first program in the repo there. It's called fork, and experiment with what happens with values of variables. Remember how I said each process gets its own copy of the variables? So that'll be the first one. They all just seem like a few lines, but there are a few difficult lines sometimes. Yeah. All right, hack away. This stuff in that this repo, sorry, this repo is a 2-day thing, so today and tomorrow, for the record. But hack away on it early, and then I can answer questions early. I have one final caveat. This won't work if you're on Windows and you're running MinGW. You need to be running WSL or Cygwin. MinGW doesn't support fork. Other than that, all right, gang, I'm gonna head off. Thanks for listening. This went a little longer than I wanted, and it was my fault for not giving you guys those 2 videos to watch ahead of time. So I apologize for that. But now I'm pretty sure you have all the videos for the whole week. So, all right, have fun. Don't fork bomb your computers. At the school I went to, they didn't allow us to use the mainframe for assignments like this. Students were banned from using the mainframe because invariably somebody would fork bomb the mainframe everybody was using, and that would be the end of it. So we all had to use individual machines that were isolated from the rest of the systems. But you'll be fine. All right, gang. Have a good lunch. Talk to you soon.